Welcome. Let's take a look at hyperbolic functions. Hyperbolic functions are functions that share properties similar to those of trigonometric functions, but they are built from exponential functions. We can see here in the table there are 6 hyperbolic functions. We have the hyperbolic sine, often referred to as sinh. We've got the hyperbolic cosine, often referred to as cosh, the hyperbolic tangent, tang, cosecch, cosecant hyperbolic, setch, hyperbolic secant, and cosh, hyperbolic tangent. Now you'll notice in the definitions here of each of our hyperbolic functions, the exponential function. So for example, the hyperbolic sine or sinh is e to the x minus e to the negative x divided by 2. The hyperbolic cosine is e to the x plus e to the negative x divided by 2. The hyperbolic tangent, much like the trigonometric tangent, is sinh over cosh. And notice that these reciprocal relationships mirror those that we see in the trigonometric functions. Notice that there is a domain restriction for the hyperbolic cosecant, the hyperbolic secant, and the hyperbolic cotangent. That is, x cannot equal 0. If x was equal to 0, our denominator would be e to the 0 minus e to the 0, or 1 minus 1, which is undefined. So while the hyperbolic sine, cosine, and tangent do not have any domain restrictions, their inverse functions do. Now in trigonometry we learned that the point cosine of t, sine of t lies on the unit circle, which can be described by the equation x squared plus y squared equals 1. Well, there's a similar relationship for the hyperbolic cosine, cosh, and for sinh. And that relationship is that the point cosh of t, sinh of t, lies on the right branch of the hyperbola x squared minus y squared equals 1. Now, if we were to graph that entire parabola, there would be a mirror image on the left side of the x-axis. However, cosh of t is always positive because cosh of t is equal to e to the t plus e to the negative t over 2. And both of these exponential functions are always positive. So cosh of t is always positive, and cosh of t is the x-coordinate of this point. So we only get the right-hand branch of the hyperbola x squared minus y squared equals 1. Now let's take a look at some of the graphs of these hyperbolic functions. The graph of the curve hyperbolic sine or sinh of x is here in black. Notice that the hyperbolic sine function is e to the x minus e to the negative x over 2. Now we could rewrite this function as e to the x over 2 plus negative e to the negative x over 2. And in doing that, we can think of our sinh function as being the sum of 2 other functions. And those functions are pictured here in our graph in red. Our sinh function is the sum of y equals e to the x over 2 and y equals negative e to the negative x all over 2. So if we could go point by point wise through this function and see that for each x value, if we add the corresponding y values for e to the x over 2 and negative e to the x over 2, we would in fact get the y value that we see graphed here in our Setch function. For example, at x equals 0, we would have positive 1/2 plus negative 1/2, which would give us a point on the graph of the Setch function of 0. A couple of other details. The domain of the Setch function is all real numbers, so from negative infinity to infinity, and the range of the Setch function is also all real numbers, so negative infinity to infinity. Next, let's look at the hyperbolic cosecant, cosetch. Now, cosetch is 1 over Setch, and notice that x cannot equal 0. If we were to write this function in its exponential form, we would have 2 over e to the x minus e to the negative x. And notice that a value of x passed through this function would create a 0 in our denominator. So let's notice then here at 0 on our graph that we have a vertical asymptote at x equals 0. The curve here in red is y equals sinh of x, and we should be able to see that inverse relationship between, or that reciprocal relationship between the y values of the sinh function and the y values of the cosetch function. So to kind of illustrate the reciprocal relationship between the two curves, for example, when the hyperbolic sine is equal to 2, so our y value is equal to 2, we can see that that corresponds to a y value of 1/2, or the reciprocal of 2, for the cosetch function. We can also see that over here in the negative x values, when our y value for the sinh function is negative 2, we can see that the corresponding y value for its reciprocal function, cosetch, is negative 1/2. Let's also observe the domain of the function. So the domain of the cosetch function is negative infinity to 0, union 0 to infinity. Remember that vertical asymptote that occurs at x equals 0. The range of the function, cosetch, is negative infinity to 0, union 0 to infinity as well. And one last attribute of the cosetch function is that as x tends to positive infinity and as x tends to negative infinity, we do have a horizontal asymptote of y equals 0. Now let's take a look at the Cosh function. The Cosh function is equal to e to the x plus e to the negative x over 2. We could separate that like we did for sinh, and we'd have e to the x over 2 plus e to the negative x over 2. So over here on our graph on the right, we have included these two components. So we would have y equals e to the negative x over 2 and y equals e to the x all over 2. And now Cosh is the sum of those two function values. So for example, we could look here where x is equal to 0. And where x is equal to 0, both e to the x over 2 and e to the x negative x over 2, return a value of 1/2. And so we would be adding 1/2 and 1/2, which would give us a function value for Cosh, 1/2 plus 1/2, or simply 1. Now let's note that the domain of the Cosh function is all real numbers. However, the range is from 1, including 1, to infinity. Now let's look at the Setch function. Recall that the Setch function is the reciprocal of Cosh, and if we were to write this in its exponential form, we would have 2 over e to the x plus e to the negative x. And Setch, as we see here, is the reciprocal of the Cosh function. So our Cosh function is here in red, and our Setch function is provided in black. Now, the domain of the Setch function is all real numbers. So domain is negative infinity to infinity, and the range is from 0 to 1, not including 0. So a couple things to notice. We do have a horizontal asymptote as y heads to either positive infinity or negative infinity. Our asymptote is y equals 0. And we can see this reciprocal relationship between the Cosh function and the Setch function. For example, when Cosh is equal to 2, then Setch should be equal to 1/2. And so, or the reciprocal of 2. And we can see that borne out in our graph. Same here when Cosh is equal to negative 2. We can see that the reciprocal, which is negative 1/2, is the corresponding point on the Setch function. Next, let's look at the hyperbolic tangent function. The hyperbolic tangent function is the ratio of the Setch function to the Cosh function. If we wish to write it in exponential form, it would be e to the x minus e to the negative x divided by e to the x plus e to the negative x. So notice it's the ratio of the hyperbolic sine and the hyperbolic cosine. Now we have graphs for both of those over here in red. So the curve that resembles a parabola but is not a parabola is the Cosh function. And the curve that resembles a cubic function but is not a cubic function is the Setch function. And so tanh is the ratio of those two. We can see that borne out, for example, at x equals 0. At x equals 0, the Setch function we can see is 0. And we can also see that the Cosh function is 1. So from our graph, we can deduce that the tanh of 0 is 0 over 1, or simply 0. And we see that point where this curve crosses both the x and the y axes. We can also notice that the tanh function has two horizontal asymptotes, and it has a horizontal asymptote at y equals 1 and another horizontal asymptote at y equals negative 1. The domain of the function is all real numbers, but we see that the range is bound between these two horizontal asymptotes. So the range will be from negative 1 to 1. Lastly, we have Cosh. Cosh is the hyperbolic cotangent. It is the ratio of Cosh and Setch. It is also the reciprocal of tanh. So over here on our graph, we see that we have y equals tanh of x in red, and then our y equals cosh, or the hyperbolic cosine of x, in black. Now notice that because the hyperbolic tangent at 0 is 0 and cosh is the reciprocal of tanh, that we will have this vertical asymptote at x equals 0. Also notice that those horizontal asymptotes at y equals 1 and y equals -1 are maintained as well. So we end up with a domain for cosh of -infinity to 0, union 0 to infinity, and a range of -infinity up to -1. Notice that there are no y values for the Cosh function between -1 and 1, so union from 1 to infinity. So hyperbolic functions are useful in modeling what is known as a catenary. Here's a couple of images of catenaries. This spider web between any two vertical strands, we have a catenary. Here's an example of a catenary that's a chain between two posts. So a catenary is a curve that a hanging chain or a cable, under ideal conditions, will assume due to being supported only at its ends and bearing its own weight. So let's go ahead and take a look at this catenary on the right. Let's zoom in a little bit and take a look. We have two curves here. The curve in red is the catenary that models the chain very well. You can see that this red curve comes along and models the chain very well. The blue curve, G, is a parabola. The parabola comes close to modeling the hanging cable, the hanging chain, but it doesn't do as good a job as the catenary. We can see a difference between the two curves here, specifically where the chain connects to the posts. The quadratic function, the squared function, just does not do a very good job, and the catenary, though, is the ideal function for modeling this behavior.